we're going to talk about the conservation of mechanical energy. And we'll review a little bit, the kinds of energy we have and what we mean by energy. Then we're going to define mechanical energy. Like, what do we mean when we say mechanical energy? And then we'll talk about when is mechanical energy conserved. Well, if you have conservative forces, it'll be conserved. If you have non-conservative forces, they won't be. Mechanical energy won't be conserved. So we'll talk about that. Then we'll talk about a particular problem that's very common, and it's the roller coaster. The roller coaster, and we'll finish with Mr. Lake's Wild Ride, which is the magical ride of the imagination that never exists in nature. All right, so let's begin. Let's review a little bit. We have energy, right? You can change stuff. Energy changes stuff. If you don't have any energy, you can't change anything. Okay, so now we have different ways of storing energy in the environment. Okay, we had kinetic energy. And I'm going to do something mean right here. I just decided to do it. I'm going to use the variables K and U. And they're not going to match the variables in your book. And the reason why is I found out that the variables that they use on the AP test are K and U rather than KE and PE. So let's make that switch now. We have kinetic energy. We have an expression for it. 1/2 the mass times the velocity squared. If I do work on an object, if I have a net force and I do work on the object, I will change the kinetic energy of that object. Let's say an object was at rest, but I applied a net force to it and I pushed on it through a distance. We found out that the result of doing that work, that force times distance, resulted in the object, this massive object, having some speed. And because that object now has mass and speed, it can now do work somewhere else. So kinetic energy is a way that energy is stored in an object because it's moving and has mass. Then we had U sub G, and there's the variable change, I'm sorry. U sub G. This is gravitational potential energy. Okay, and I'm just doing that to define the variable. So U sub G, the equation for it was mg. You can use y or a. I'm going to use h. H is the height above or below the reference, where you measure height from. So your height can be negative if you're below the reference. If you dig a hole in the ground, jump in that hole, you have negative gravitational potential energy compared to the ground, and so on. Then we had U sub E. So again, this is a variable change from the book. This is elastic potential energy. And so U sub E, we derived an expression. It's 1/2 K x squared. Now here's where you have to be really careful. What does capital K stand for? Kinetic energy. What does lowercase k stand for? Spring constant. Different things. This has units of newtons times meters, joules. This little k has units of newtons per meter. Okay? How many newtons of force you need to stretch or compress an elastic material by 1 meter? Okay? Well, now let's define mechanical energy. Mechanical energy. Now, there's lots of different kinds. There's thermal energy, internal energy, electrical energy, chemical potential energy. There's lots of different kinds of energy. But here we have these three. So what we define is this. We define mechanical energy, and we're going to use capital E to represent mechanical energy. It is simply the sum of an object's kinetic energy plus its gravitational potential energy plus its elastic potential energy. Okay, this is by definition. It's equal because we say it's equal. We are defining it to be this. Okay, so and let me show you how this, an object that might have all three kinds of energy. Suppose I have an object on an incline like this. Okay, and this has some angle theta, and I have a little car on a track. It has mass. Let's say it's moving down the track, so it has velocity. Let's say it's anchored to a spring like this, and it's stretched that spring. That spring has a spring constant of K. Also, it has a certain height above the ground, above our reference. So this thing is moving, it's stretched a spring, and it has height above the ground. If we add all that up, well, let's see, this would be 1/2 mv squared plus mgh plus 1/2 kx squared. And that'll be the total amount of mechanical energy in the system. Now, I could give you an example, and we could go through all the math, but we're kind of running low on time. So I'm just going to say, hey, when we say mechanical energy, we mean all the potential energy, gravitational potential, elastic potential, and kinetic energy, just all added up. Okay. Now, let's think about the work done. The work done by gravity. Okay, so suppose I have an object. We'll just use the bowling ball. I'm holding a bowling ball, and here's the ground. So this is the original height. We'll call that h1. And then I drop it. I release the bowling ball, and I look at it. Oh, maybe it's down here. Okay, and somehow the bowling ball got smaller. All right, so do you see that the bowling ball lost gravitational potential energy? Let's take a look at the change in gravitational potential energy. Okay, so well, it's mgh2 minus mgh1, right? This is h2. So going from h1 to h2, well, this is mg delta h, isn't it? Mg delta h. You see that there's delta h. Does that make sense? Okay. Now, let's take a look at the work done by gravity. I'll put W grav. Okay, the work done by gravity is, well, look at the force, right? The force of gravity is straight down. And the distance it's fell is straight down. So this is mg times delta H times the cosine of the angle between it. But this right here is the magnitude of the force of gravity. We don't put the negative there. The delta H, that's the magnitude of my change in position, right? Work is force times our change in position times the cosine of the angle. But this is the magnitude of this force, the magnitude of this. So this delta H here is not negative. And what's true about theta here? If the force is down and my change in position is down, do you see that gravity is doing positive work? Gravity is doing positive work. Okay? But this is the work done by gravity. But notice up here, this expression. It looks like the same expression as this, but it's not. Because this delta H is negative. So this is going to be equal to this is a change in potential energy. But here's the deal. Yes. Oh, thank you. Yeah. You got to let me know if I'm off screen, man. Okay. So, and here's what it's kind of difficult to mathematically rigorously go through this, but here's what I want you to see. Do you see that gravity is doing positive work? Right? But when gravity does positive work, you lose gravitational potential energy. This delta U will be a negative. And when gravity does positive work, potential energy is lost. I want you to see that conceptually. You drop something, for crying out loud. Gravity's pulling it down. The displacement is down. Gravity's doing positive work. But what is the source of doing that work? Remember, work is a transfer of energy. We are taking the gravitational potential energy and we're losing it, right? The gravitational potential energy is being used up. Now, as this bowling ball falls down, do you see that this is the only force doing work? So the work done by gravity is equal to the work done by the net force. Well, that's going to be equal to the change in kinetic energy. Does that make sense? Okay? Think about that. This is the Work-Energy Theorem. We developed that the other day. Well, the change in kinetic energy is going to be equal to the loss of potential energy. Okay, we said that the work done by gravity is going to be equal to this loss of potential energy. See, in order for gravity to do positive work, if I just figured out mg delta H, mg delta H, well, delta H is negative here. But if gravity is doing positive work, I have to cancel out that negative by sticking a negative in here. So the work done by gravity, positive work done by gravity results in a loss of delta U. But by the Work-Energy Theorem, that loss of delta U is going to add to my kinetic energy. I hope this isn't too abstract, but this is how physicists think. So you got to follow along. Follow along. All right. So I have this very interesting expression. Delta K equals negative delta U. Well, what if I add delta U to both sides? Delta K plus delta U equals 0. Okay, this right here is super profound. Delta K, what is that? That's the final kinetic energy minus the initial kinetic energy. Plus delta U, that's the final potential energy. Did I say kinetic over here? Kinetic and potential. Equals 0. Well, now I'm going to put this on the other side. The final kinetic energy plus the final potential energy equals, well, I'm going to add the initial kinetic energy to the other side, and I'm going to add the initial potential energy to the other side. Thank you. So in this system, this bowling ball being dropped, if the only force doing work is gravity, then if I add up the final kinetic energy and the final potential energy, it'll be exactly equal to the initial kinetic energy plus the initial potential energy. But what did I say? What is kinetic energy plus potential energy? What do we call that? What did we call that a few minutes ago? We called it mechanical energy, E. Now there's no springs in this problem, so let's ignore elastic potential energy for right now. This is the final mechanical energy. It must be equal to the initial mechanical energy. So in this system, where I'm just dropping an object, what are we ignoring here? You would not be able to do this with a feather.
Air resistance.
Because air resistance is significant. We're assuming that air resistance on the bowling ball, for just dropping it on, from a normal, air resistance is negligible. It's so tiny that we just can forget about it. So, the final if and only if the only force doing work is gravity. Have you seen that if and only if before IFF? Yeah. This is a big deal. If the only force doing work is gravity, then I can say the final mechanical energy is equal to the initial energy, and I can use that to solve problems. Now let's look at a spring. Now I'm not going to go through it quite as much detail as this, but if here we have a spring, and let's say when you're right here, it's 0. That's where the spring is relaxed. It's not stretched anymore. So it would have 0 elastic potential energy. Now let's push that spring in like that, and so now the spring is all compressed. It's a compressible spring, and let's say it's got a little plunger-like thing, and let's say right here is a marble or something, like a marble shooter. You compress it. Now, if the spring does work, okay, when the spring does positive work, okay, So look at the spring right here. Do you see that it's pushing on this ball or this little marble or something? So there's the force of the spring. And it's going to push it through this displacement. We'll call this delta x. Well, from here over to here, actually. So the change in position vector is in, so the force and the change in position vectors are in the same direction. So the spring is going to, from here to here, the spring is going to do positive work. But what is potential energy? Let's take a look at the change in potential energy. The change in potential energy of a spring is, well, we know that that's going to be equal to 1/2 k, or 1/2 k x final squared minus 1/2 k x initial squared. And if it goes from here to here, x final is smaller than x initial. So if the spring is doing positive work, we're losing gravitational potential energy. But if the spring is doing positive work, it's adding kinetic energy. And the work done by the spring is if that force of the spring is the net force on that object, then the work done by the net force is going to be equal to the change in kinetic energy. But the work done by the spring comes at the expense of the potential energy stored in that spring. So this is going to be equal to the loss of potential energy in the spring. This is exactly what we did with gravity. So we can say, well, delta K equals negative delta U. So this is K final minus K initial. Oh, add it to the other side. So delta K plus delta U equals 0. So plus, I'm trying to go too fast. U final minus U initial equals 0. So now I'm going to put the final stuff over here. Okay, and what would this be, by the way? This would be 1/2 mv final squared plus 1/2 k x final squared equals 1/2 mv initial squared plus 1/2 k x initial squared. It's a lot of writing, sorry. Well, this is the total mechanical energy. This is the kinetic energy plus the potential energy. That's E final equals E initial. So this is true if and only if the only force doing work is the spring. Okay? But what if you have gravity and springs? It works the same. It works the same way. So, everybody done with that? Okay, so this would be the last. We're finishing up now. Okay, so if and only if, look, I wrote out the whole thing. That's how important this is. The only forces doing work are gravity the force of gravity and springs. And when I say springs, I also mean rubber bands and bungee cords, any elastic materials. Then E initial equals E final. So you look at a problem and you say, what forces are acting in this problem? I got a spring, and the spring is the only thing doing any work. Or I have gravity. Gravity is the only thing doing any work. Well, then you can say mechanical energy is conserved. And you start here. And you say, well, this is kinetic energy plus gravitational potential energy plus elastic potential energy equals the final plus UG final plus UE final. And look, this gives you an equation that you can use to solve a problem. And it's awesome. It's so much better than using force. Whenever I do a problem, a physics problem, I look at it and it's like asking me for the final velocity or how high something goes or whatever, I always ask myself first, can I use energy to solve this problem? Because energy is almost always easier than using force and kinematics and all that sort of thing. Because we know that this is 1/2 mv squared, this is mgh initial, this is 1/2 x, 1/2 kx initial squared, and the same thing's true for those finals. So all you have to know is where the object was at the beginning and where it ends up, and you can solve for whatever unknown ends up being in that equation. Awesome. Really, really, really powerful problem-solving tool. Okay. Now, I'm just going to talk briefly about conservative versus non-conservative forces. Okay, and we'll cover this again later, and I think I'm going to save the wild ride for next time. Mr. Lake's wild ride for next time because it's just a roller coaster idea, but. Conservative forces don't change mechanical energy. Okay, but here's what they do. If you imagine you've got energy, you've got K initial plus UG initial plus UE initial. Think of these as like little containers that hold energy. They store energy. You store energy in motion. You store energy in a gravity field. You store energy in that, in elastic material. If you have a conservative force, what a conservative force does is, let's say you're coasting up a hill. If you're coasting up a hill, what's slowing you down? Well, a component of gravity is slowing you down. As you go up, you lose kinetic energy. So you lose kinetic energy, but you gain gravitational potential energy. So this is the work done by gravity. This arrow represents a transfer of energy from one container into another. And here, gravity is slowing an object down. It's taking away its kinetic energy, so it's doing negative work. When gravity does negative work, you gain potential energy. Or let's say you have an object that's running into a spring, and that spring is slowing it down. Well, that spring can take away its kinetic energy. And or you can go the other way around. So this is the work done by gravity. This is the work done by springs. And all they do, all the work done by springs or gravity is transfer the energy back and forth from kinetic to potential to elastic. But all you're doing is pouring that energy into a different container. Non-conservative forces add or subtract mechanical energy from a system. For example, well, here's a couple of examples. These are the big ones, and I'm going too long. So, like applied forces. Okay, you ever push a little kid on a swing? Okay, to get the kid going, okay, the kid, you got to push on their back, right? You got to add energy to their system so they'll start swinging. Oh yeah, Daniel, you.
Daniel's not here.
Oh, Daniel's not here. Yeah. Okay. Applied forces. If you push on something, you'll add energy, or you'll take its energy away. Friction. Friction is something that will take, quite often will take there's one exception to this, but for most, like if I push on an object and it slides to a stop, the object lost mechanical energy because friction turned it into the random vibration of molecules. It heated up the environment. Okay? So non-conservative forces add or subtract mechanical energy from systems, but conservative forces don't change the mechanical energy. They just change where that mechanical energy is stored. Like gravity can turn kinetic energy into gravitational potential energy and vice versa. Okay. And elastic can do the same. Okay. That's kind of a lot. I don't like going half an hour, but it must be done. So use this. This is where you start a problem if the only force doing work is gravity or springs. And then in the next assignment, we'll talk about how to handle stuff where there are non-conservative forces involved. But make sure you understand how we define mechanical energy and the circumstances under which mechanical energy is conserved is that if the only forces acting are conservative forces like the force of a spring or the force of gravity. That is all.